Well, our next speaker is Ahmad Salmanogli. I would read it Ahmed Salmanogli. I'm sure
Yeah,
that our
yeah,
colleagues
correct,
pronounce in this way. Welcome,
correct.
Ahmed. You can share your screen, I think.
Yes, if you
Okay.
let me, I am
So,
trying
hmm,
to share the screen with you. Okay. I think,
oh,
yeah.
okay. So it's 20 minutes. I will just remind you that you have 5 minutes left. Okay. And
That's okay.
people can ask their questions through chat box as usual. So Ahmet Salmanoglu from Çankaya University will talk about an interesting proposal, an interesting subject from many points of view, which is quantum radar. Okay, thank you.
Thank you. Thank you for your introduction. I appreciate that. And okay, the design of quantum radar from quantum theory to an operational point. Our presentation contained two different sections. Part one, a general schematic for quantum theory and using the quantum theory to model quantum radar. And in part two, we discuss about the conceptual design of a quantum radar, and I think it will be very interesting for you. Okay, let's start with part one. And quantum radar can be defined as a kind of measurement system like a classical radar. It is because the quantum radar using the microwave photons, but moreover utilize another factor such as quantum phenomenon factors such as entanglement to improve and enhance the target detection and recognition performance. A simple definition about the quantum entanglement. Okay, let's start on our our new idea, the optoelectronic based quantum radar. As you can see here in this section, we replace the traditional electro-optomechanical system with our new design. I mean, optoelectronic system. It is due to some facts. One of the important facts is related to the mechanical part that in the traditional system, mechanical systems or subsystems operate at low frequency. Low frequency means a lot of thermally excited photons can be entered to the system, and thermally excited photons means that we can easily lose the entanglement. Okay, let's start with this optoelectronic based quantum radar. The operation starts with the interaction of a high density laser with the optical parametric down converter material, and two photons, signal and idler, is created. They're entangled with each other. We keep the idler in the lab and use the signal, and this is our optical cavity, and the optical cavity output mode coupled to the photodetector. And in this idea, we use the quantum dot-based photodetector to enhance the sensitivity of the photodetector. So by coupling of the optical cavity to photodetector, a photocurrent is flow in the circuit, and by flowing the photocurrent here, a voltage drop across the varactor diode. This is the varactor diode we used in the system. By changing the optical current, which is a function of the coupling of the optical cavity with photodetector, voltage across the varactor diode is changed. By changing the voltage across the varactor diode, a depletion layer of the varactor diode will be changed. And change of the depletion layer varactor diode means the change of the capacitance induced by the varactor diode. So this is our microwave cavity. By change of the capacitor, LC resonator characteristic will be changed. Okay, we will try to use this optoelectronic system to generate the entanglement between microwave cavity mode and optical cavity mode. And this is our microwave cavity output modes. And before to propagate through the atmosphere, we need to intensify this signal, and we will use the, for example, transmitter. And by propagation of these modes, the intensified modes through the atmosphere. This is the atmosphere. In this idea, we used some beam splitters in series to model the atmosphere, and beam splitter operated as a scattering agent in the in this model. And moreover, the target scattering, this is the target model. And again, we use the beam splitter to model the target, and CT is the backscattered modes of the target. Again, this backscattering signal should be propagated through the atmosphere, and then receiver and detector. Okay, let's start the model of the quantum. I mean, in this presentation, we specifically focus on the optoelectronic converter designing, and we, as you know, to design our system using the quantum theory, we normally start with the definition of the Hamiltonian. They are contributed to Hamiltonian for each system. This is our optical cavity, photodetector, and microwave cavity, and the Hamiltonian for the optical cavity and driving field, and Hamiltonian for photodetector, and the Hamiltonian for microwave cavity. And moreover, this two important Hamiltonian, which we will use this. I mean, this one's the interaction Hamiltonian to engineer the system to create the, for example, entanglement at high temperature, and the rate of interaction between the optical cavity and photodetector. And moreover, this is considered as the microwave cavity coupling to the photodetector, and EC for driving field, and E omega driving field for the microwave cavity, EC for the optical cavity, and considered as a strong field in this system. Okay, so here in this section, optical cavity and photodetector, and the rate of the optical cavity for define the rate of the optical cavity in this system, we use the first order perturbation theory, and moreover, to define the interaction Hamiltonian between the optical cavity and photodetector, we use the dipole approximation method, and this is the result for the coupling of the optical cavity to the photodetector. Omega c, the frequency of the optical cavity, mu dipole moment, and the density of state of the photodetector, and Lorentzian function. And using this factor, which is the rate, you know, and times to the electron charge, one can easily calculate the photocurrent. And this is the photocurrent that we use to bias the varactor diode. I mean, by changing of this current, the varactor diode capacitance will be changed. And through this method, the optical cavity is coupled to the microwave cavity. And here we define the parameter as a mu c in the MC microwave cavity coupling to photodetector Hamiltonian, and it is related to the change of the capacitor in the system. Okay, so to analyze the system, we follow the procedure with the system dynamics equation of motion, AC using the Heisenberg-Langevin equation, AC for the optical cavity, C omega for the microwave cavity, and quadrature operator for the photodetector. R in, C in, and B in considered as a noise to the system. It is because our cavities, design cavity, interact with the environment. And moreover, kappa omega, kappa C, kappa omega, and gamma P considered as a decay rate for the cavities. And we need to linearize the system. It is due to these terms in the equation. To simplify the algebra, we need to linearize the system, and the linearization form illustrated here. And after that, we can calculate the entanglement between the modes, and more importantly, calculate the number of photons of the cavity. And for example, we have to calculate the number of photons of the microwave cavity. It is because after that, we need these photons, these signals, to propagate through the atmosphere to find the target. Okay, so before the propagation of this signal into the atmosphere, we need to intensify the signal, and we model the transmitter here using the beam splitter. This is the active medium, and called here active medium, to intensify the signal. And this is the microwave cavity output mode, and this is the output mode of the active medium. And here the expression that define the this term, Ca omega, the first term stands for amplification of the signal. This is MC, or microwave cavity output, and this is the amplification factor. And the second term defines the noise effect, noise induced due to the active medium to the signal. And in the same way, we model the atmosphere using the beam splitter in series, and the first terms defined indicate the attenuation factor, the effect of the attenuation factor due to the atmosphere, propagation of the signal into the atmosphere. And the second term, it is the noise induced in the atmosphere. Okay, the results of our simulation or modeling. And here the graph A is for entanglement between the optical cavity and microwave cavity, and the graph B, optical cavity and the return field. This is return field for this. The distance between the transmitter and detector is around 2 meters, and with this specification for the atmosphere characterization and target, and moreover for the coupling between the microwave cavity coupling to the photo detector. And here it is shown that with increasing the temperature, the amount of the entanglement is decreased. And moreover, in this case, here it is shown that after, after 1 K or 1000 millikelvin, all of the photons become separable. Okay, we check the, here it is the symplectic eigenvalue that we use to evaluate the entanglement here, and here it is the formula that we used. And moreover, we check this result with other criteria, such as the entanglement metric, which as you know, we use the microwave cavity, optical cavity number of photon, microwave cavity number of photon, and moreover it is the phase sensitivity between the optical cavity, phase sensitive correlation, cross correlation between the optical cavity and microwave cavity. And moreover, one can use this criterion, Simon-Peirce-Hordesky criterion, to check the result, and there is no problem with that. We calculate the entanglement with these 3 different methods. But here we replace the optoelectronic rather than the electro-optomechanic system. It is because we want to create the entanglement at higher temperature. It was the main aim of this idea. And by engineering, we found that by engineering the microwave cavity photodetector coupling factor, we can create, we can produce the entanglement at high temperature. But we know that this is just a theoretical simulation, and in the reality, generation of the entanglement as such, it is 5 Kelvin is I think it is impossible. And here the interaction between it is the rate that connect the microwave cavity to the photodetector. It depends on mu c, and mu c is a function of the optical current, and optical current is a function of the coupling between the optical cavity and photodetector, and we define the optical cavity coupling to the photodetector by this expression show GA omega p related to the GA OP. Okay, second part. In this part, I would like to discuss about our conceptual design of a quantum radar, and this is a start with the fact that we generate the I suppose that we generate the entangled photon here. The operation starts with the interaction of laser with the OPDC, IIS and II as a optical entangled photon are generated. We use this signal and generate the C omega. This is C omega. C omega are entangled with IS. We calculated here, and this the result illustrated here. And expectation value 2 eta shows that the 2 eta less than 1 means that the photons are entangled. So moreover, we calculate the number of photons of the microwave cavity, and here the number of photons for the microwave cavity, and less than 1 means that we have entanglement around, for example, the tuning frequency around 0. And moreover, the number of photons of the microwave cavity around 1 shows that our design quantum radar works based on the quantum illumination protocol. That means that there is no problem with that. And so in the following, we need to calculate the power of the power generation by this number of photon. It is around -70 dB, and that means that our microwave cavity output power is around -1700 dB, and one can use this power to directly, with no need to any transmitter, to propagate through the atmosphere to detect the target. But we know that using such this low power, all of the signal will be lost in the atmosphere. But so in the following, we need to use the, for example, transmitter in the system to amplify the signal, and this is the starting point for the simulation of the transmitter. In the transmitter, for transmitter and receiver, we use the ADS, Advanced Design System, and this is our MC system, microwave cavity system, works around 2 gigahertz. This is our signal, and this is around -1700 dB. And moreover, we generate this signal as an image of this signal, and we will use this signal in the receiver section to transfer our RF signal. This is considered as a RF radio frequency signal to the intermediate signal. Okay, so don't worry about this section, just focus on this part, 2 gigahertz with -1700 dB, and this is our transmitter. To design the transmitter, we use the ADS, or Advanced Design System. The flow chart, the design flow chart in ADS illustrated here. It is a start from the schematic design in ADS, simulation in ADS, and PCB layout generation in ADS, and this is our final point, PCB layout simulation. Usually the PCB layout simulation result is different than the schematic. It is because in the PCB layout simulation, like reality, some factors such as the interference between the microstrip lines, and moreover, we know that microstrip line in a system can be operated as an antenna, and the PCB layout simulation considered the effect of the radiation and something like that. So, and this simulation needs to some optimization, and we call that co-simulation in the ADS, and this is called redesign. And when the PCB layout simulation results are satisfactory, we can order the PCB layout and implement the system. Okay, this is our transmitter design. Here we use some elements, electronic-based elements, bandpass filter, and moreover LNA. One of the critical difference between the quantum radar and the classical radar is the LNA that we use in the transmitter, quantum radar transmitter. Normally in a classical radar, we use the PA, or power amplifier, to amplify the signal, but we cannot use the power amplifier in the quantum radar system. It is because that the PA, or power amplifier, can induce a lot of noise to the system, and the noise can easily kill the entanglement. So we need to design low noise amplifier or ultra low noise amplifier. Okay, let's start with the bandpass filter. The PCB layout of the bandpass filter illustrated here. As you can see, there is no any lumped element in the system. All of the circuit designed with the distributed element, port, input port and output port, and the characteristic of the bandpass filter. The red graph is for the reflection, and the blue one for the transmission, and centralized around 2 gigahertz. And moreover, the other important factor is the noise figure. And noise figure for this design is around 0.2, which is very good point for the bandpass filter. And
5 minutes.
Yes, okay, no problem. And the other important case is the LNA, and For LNA, the PCB layout of the LNA illustrated here. This is the input matching network, output matching network, and we use the cascade transistor to intensify the signal, and the gain of the signal, the gain of the LNA illustrated here, around the 2 gigahertz, 3 dB gain of the circuit, and the other specification of the LNA noise around 0.5. It can be considered as an ultra low noise amplifier, and moreover the reflection coefficient and other factor for LNA that we have to consider is its linearity. And for linearity, you can consider this F as a central frequency 2 gigahertz, delta F equals to 1 megahertz. So F plus minus delta F gives us F1 and F2, and some frequencies such as F1 plus F2, F2 minus F1 can be easily filtered by the bandpass filter both. There are some frequencies such as 2F1 minus F2 or 2F2 minus F1 are the frequencies that we cannot easily filter. So we have to accept the effect of these frequencies. Both we define the intermodulation distortion, and in the design of the LNA, we use some technique to increase the IAM3 to increase the linearity of the LNA, and this is the comparison between the other factor. Okay, so this is output of the our transmitter. If you could remember, we start with this signal minus 700. After transmission, the transmitter output is around the level of the signal is reached around minus 68 dB, and the characteristic and the specification of the transmitter gain is around 80 dB, noise figure of the transmitter around 1 dB, and the reflection coefficient. Okay, come back to our original slide, and here the output of the transmitter reached to the other mode. You can also consider the other mode and our original mode, and minus 86 dB, and considering this target with RS 0.1 square meter, and using this equation, the range of the signal after this 2 meter and 2 meter here reach to minus 2200 dB, and this signal needs to amplification again, and this is the receiver that we used. The first part is designed as same as the transmitter section, but the second part relate to the IF signal, and I need to consider this. It is due to the fact that the frequency is different than the IF frequency. Here, the IF frequency, intermediate frequency, is considered as 0.6 gigahertz, and filter that we used here, it is the PCB layout of the filter and noise figure and the scattering parameter, and moreover LNA that we designed at 0.8 gigahertz. The noise figure of the LNA, you can consider that at 0.8 gigahertz it is around 0.5 dB, and moreover this is the result for the gain is around 48 dB, and the stability factor and linearity of the receiver. And here this is the input for the input signal for the receiver, minus 2200 dB at 2 gigahertz, and after amplification it is reached to minus 100 dB, and this is the signal IF signal. It is around 0.8 gigahertz, and after amplification the level of the signal reached to minus 33 dB. Okay, so come back to our original slide, and so here after receiver the level of signal reached to minus 33 dB. Okay, so here this is the signal that we use to make the cross correlation with the signal that we kept in lab, and by this signal, our signal to noise ratio for this system, for this conceptual design, reached to minus 20 dB. Okay, thanks for your attention, and we are so happy to be a part of COVID-5.
Thank you very much. Thank you.
You are welcome.
We have maybe you already know them, some experimentalist colleagues, also engineers as well in our audience, and they already have some questions.
Okay.
We have a question from Bulat Rami from Gebze Technical University. Bulat Hoca asks, have you calculated the conversion efficiency of your optical to microwave converter concept?
So, I think the question is about this part. Here, to calculate the optical cavity coupling to the photodetector, we use the first order perturbation theory, and moreover, H interaction, the Hamiltonian, the interaction Hamiltonian here, we defined, we use the dipole momentum to calculate the H interaction. So using the first order perturbation theory, we define the rate of coupling between the optical cavity to photodetector.
Okay. Thank you. We have another question. You can also read the question if you want from the chat box, but I will read for everybody.
I have to.
Yes. This is from.
Okay.
Yeah, Burak Aktu Yilmaz is from Aselsan. In transmitter and receiver parts, there can be lots of impedance mismatching matching problems.
Okay.
I see from your schematic sheet, all elements have chosen as ideal. Do you have their measurement results? Do you have chance to use their these two key parameters in your simulations? If you can read the question,
Yeah, I got the point. Okay, if you let me, I need to go to the transmitter and receiver section. Here it is. And if you let me, in the transmitter, first of all, our simulation is not just in the schematic. All of them is PCB-based modeling, I mean momentum simulation. And here, if you could, for LNA, I need to, here. In this section, we use the input matching network to minimize the reflection from input, and moreover, output matching network to minimize the output reflection. So using this in systems, I mean input matching network and output matching network in the system, we could minimize the reflection. And moreover, if you consider these results this one, and this is the simulation of all of this part, I mean transmitter, PCB-based transmitter, and the reflection coefficient for around the 2 gigahertz. You can consider this part, I mean, for input reflection, S11, it is around minus 15 dB, and for S22, I mean, the output reflection is below than the minus 20 dB. I mean, it is perfect for a transmitter to minimize the reflection. And the other question
there is about some bandwidth question. There is also at the end of the same.
This is and additionally, your bandwidth is very narrow. Is it actually, we need to choose a narrow bandwidth in quantum radar. It is because it is in contrast with the classical radar. In quantum radar, we need to choose the very narrow bandwidth. It is because by increasing the bandwidth of the system, you know, the signal to noise ratio will be decreased, will be strongly decreased. And moreover, by increasing the bandwidth of the system, for example, receiver, by increasing the bandwidth of the receiver, a lot of noise can be entered to the system. And moreover, from other point of view, when we increase the bandwidth of the receiver, the other signals, for example, you can consider the jammer, can easily jam our systems. Okay, so due to this fact, we have to consider the very narrow bandwidths for our system in quantum radar that, you know, the entanglement is very fragile, is a very fragile phenomenon and can be easily distorted by noises. Okay. Other question. Is there any advantage for atmosphere propagation in using entanglement in frequency or polarization or time? We check the entanglement at each level of the quantum radar. If you let me, I need to show this part. Okay, so our results here. This, if you consider this part, it is the entanglement between the optical cavity, the graph B, display the entanglement between the optical cavity and the return field for 2 meter, I mean the propagation of the signal into the atmosphere for 2 meter. And theoretically, it is just theoretical results. And theoretically, we show that by changing the, I mean, using the optoelectronic signal, we can, optoelectronic converter, we can enhance the entanglement when we propagate the signal into the atmosphere. But I don't know if I correctly understand the question or not, but if it is not the right question, you can, I mean, repeat your question again, and I will try to answer to this question. Okay.
Thank you very much. There was one last part from the previous question, which is repeated about the range.
Range of our conceptual range is around 4 meter. 4 meter. We do our conceptual design for just 4 meter, but by increasing the range of the system, the signal to noise ratio, I think you know about, is a very important factor. And by increasing the range of the signal, I mean radar system, this factor is strongly decreased. And due to this fact, we limited our design to very short range. Okay, thank you. Yeah, the second part compared to traditional radar, I think it is not comparable with traditional radar. I think you are talking about the classical radar. For a classical radar, here for example, 2 meter, we just try to keep or save the signal to noise ratio, and moreover, quantum correlation between the signal. So for this reason, we cannot compare our results with the classical radar that use for the classic correlation. We do the quantum correlation. I mean, we have to do the quantum correlation and preserve the quantum correlation. Okay. Thank you very much. We thank Ahmad Salmanogli for this very nice, interesting presentation. Thank you very much. I appreciate that. Thank you. Thank you so much.